So in this lesson, we're going to talk about limits at infinity. That is, if we have a function f of x, what could we tell about the limit as x approaches negative infinity of f of x, or the limit as x approaches positive infinity of f of x? Well, one of the most basic things that we do is we take a look at a function like this one. Let's say we talk about the function f of x equals 1 over x squared and examine what happens to it as x tends to get large. When we say x approaching infinity, and infinity is not a value that we can attain. For example, x could approach 3 and actually be 3. X can approach infinity, but x can't actually be infinity. Infinity just means growing without bounds. So what does that mean to us? Well, if we take the values of x right here, let's say as we go towards positive infinity, starting at 0, which is undefined in this function, we see that the values of x, as they get larger, cause the values of y to tend to get much smaller. And in this case, what we're saying is that it looks as though if we could continue on to infinitely larger and larger numbers, that the value of y would eventually get so close to 0 that it would be indistinguishable from 0. And the graph, as you watch x tend towards positive infinity, tends to do exactly that. Y tends towards 0. Then we also look at going to the left, and what happens as x goes to values that get smaller and smaller. That is, as x goes to the values to the left towards negative infinity. And we see that exactly the same thing is going to happen. 1 over x squared tends to also get smaller and tends to 0. So we say that y tends to 0 in this case. So if we had stated the function limit as follows, the limit as x tends to negative infinity, which is the way that we write this, of 1 over x squared, we should be able to say 0. And likewise, if we were to state the limit as x tends to go to positive infinity of 1 divided by x squared, we say that limit is also equal to 0. And this gives us two principles that we can work with. The first one is this. If we have x raised to a power, actually let me get a highlighter out here, let's try that. If we say that we raise x to a power where that power is greater than 0, then the limit as x tends to negative infinity will go towards negative infinity if the power is odd, or it will go towards positive infinity if n is greater than 0, if n is even. On the other hand, if we let x go towards positive infinity when n is greater than 0, then pretty much always the case that the limit as x approaches infinity of x to that nth power is, where n is greater than 0, is going to be positive infinity. So if I had just a really basic example, like the limit as x approaches negative infinity of negative 5 times x to the third, we could use this principle by saying that, well, this is really the same thing as the constant negative 5 times whatever happens from our limit, and we would take that limit as x approached negative infinity in this particular example of x to the third power. And the rule here said that, well, as x tends towards negative infinity, x to the nth for an odd power goes towards negative infinity itself. So this is really similar to saying negative 5 times some number growing without bound in the negative direction, that is to say negative infinity. And so our limit is also negative infinity, is a positive infinity, because a negative times a negative gives us positive. Now, the following rule is the one that's really the most useful to us when we have rational functions and we're looking for the limits at, and I put that in quotes, infinity, because we're letting x approach something very, very large. And the rule goes like this. As x tends to negative infinity of c over x to the n, it doesn't matter whether we have an even or an odd power. The entire expression is going towards a fixed value over a very large value, and that tends to 0. And that's for positive infinity as well. So, for instance, if I were to ask you to find the limit as x tends to infinity of 4 over x to the 6th, well, you should say that this limit is going to go towards 0, because that's just by the rule right here, right? We can see that what would happen is that x would get very, very large, 4 would stay fixed, and in comparison, 4 divided by a very, very large number would be very, very close to 0. So we say that's our limit.